So my name is Uwe Riechert. I'm with ABB, and it's a pleasure for me to give you some information about the work package 11, which is dealing with gas insulated switchgear. So you could see here a picture of our last demonstration in February this year, together with the circuit breaker. And behind the group of experts, you can see the DCGRS. That is a long-term test running of the KEMA laboratories since more than 1 year. And I will give you some more information about that, what we have done in our work package related to gas insulated switchgear. So the technology gas insulated switchgear is not really new. So that is well proven since more than 50 years. As well, you can see here on the left side one picture of a 550 kV AC GIS, and looking back, we have around the world more than 100,000 GIS bays in operation. The first one was installed in 1967, so more than 50 years ago. There are a lot of advantages if you compare this gas insulated technology with the air insulated technology, where you can have also a look on the other picture where you can see an air insulated switchgear and the same switchgear using gas insulated technology. So the main advantage of using gas insulated switchgear is the massive space saving. So we can say up to 90% is the space saving compared to area insulated technology. Another advantage is the robustness against environmental impacts. And these both advantages makes it also favorable to use gas insulated switchgear, especially for offshore applications, where the space requirements one of the most important requirements. Typically, we are using SF6 up to today for this gas insulated switchgear, but we are looking also to eco-friendly alternative solutions to reduce the content of SF6 in switchgear. If we are talking about a DC switchgear, that is a little bit different to the AC version. There is no circuit breaker. If you remember the presentation from René, that's not so easy to use the gas insulated version for a breaker. So we are focusing on all other components. The typical components you can see here on the right side, starting from the left, that is the cable termination. So the connection from the GIS to a cable. That's very important for the offshore applications. We have a lot of bus bars and connecting elements, a current transformer, a current measurement, a voltage measurement, typically for DC, it's an RC divider, surge arrestor, some switching elements, so a disconnector here and an earthing switch, and a bushing, so the connection to other HVDC equipment. Good thing on the work package itself. So we have started with the first task, meaning the definition of the specification and the definition of the long-term test requirements for HVDC GIS. At the same time, we have started also another task dealing with monitoring and diagnostic methods for HVDC equipment. What is the difference to that what is known from the AC GIS? And we have also one subtask dealing with the replacement of SF6. The question, can we really use other gases as known from the AC side also for HVDC GIS? The biggest part of the work package was the demonstrator itself. So we have built up a long-term test device. And we have already performed these long-term tests. I will come back to the details of these long-term tests in some minutes. And the last task was, of course, summarizing all the results from the different tasks and give the recommendations for a standardization. On the right side, you can see here the partners of the work package. WP11-3 So we have also TSOs and different institutes in our work package. Here you can see the test device, the HVDC GIS, that's rated for 350 kV DC. The test device itself for this long-term test was defined in our work package. At the end, it is a 13 meter long and 13 by 7 meter long ring arrangement. We have one bushing to connect the voltage sources, so the DC voltage source as well as the impulse voltage source from the lab. Another bushing for tests across the disconnector switches. And we have formed a ring to create a current inside this loop here. And the current, that is an AC current, so we have used 3 conventional AC current transformers to create a current of 4000 amps AC. That is a requirement, especially for DC testing, to have a full load during testing, because the temperature, especially the temperature difference between the inner conductor and the outer conductor, is of main importance for the field distribution. So we have under DC conditions a completely different electrical field distribution under no load and under load conditions, depending on the temperature distribution. Therefore, we have also defined different cycles without load and with load to cover all the different field conditions under real situations. Moreover, you can see here the voltage and the RC divider voltage measurement, as well as the current measurement. That is a zero flux sensor in that case. Moreover, we have some disconnectors and earthing switches, so in total 3 here. A lot of monitoring and diagnostic devices, so partial discharge measurement, temperature measurement, current and voltage measurement, and also arc detection equipment here. The next slide shows the test procedure for this long-term test. If you look to these test procedures, then you can see some similarities to a test well known from a cable as a pre-qualification test. But the idea behind the pre-qualification test for cable is different to that what we have developed for GIS. So for cable, that means mainly aging of the polymeric material and mechanical stress due to different thermal situations. For a GIS, it's known from the AC side that the aging is not a real issue for the GIS and for the gas itself. Therefore, we have focused to cover most of the different typical situations during a real operation. And we have defined in total 6 load cycles without any current or with current, different DC polarities, and each cycle has a duration of 60 days. So in total, we cover nearly 1 year with these 60-day cycles. 60 days was chosen to cover the time required to reach the DC steady state for the installation. We have added 1 cycle with load cycle tests, specially defined from real experience from an offshore platform. And before starting the test, we have made some pre-test and defined also some pre-test, including polarity reversal tests. And also after the tests were defined some subsequent tests as a verification of the performance of the DCGIS. From the technical point, one major difference between cable test and HVDC test is the superimposed impulse voltage test after each cycle. So we have added a lot of these superimposed impulse voltage tests because that is the most critical test for a DC GIS. Therefore, that was added one impulse test after each cycle. Of course, we have also added AC/PD measurements and DC/PD measurements after each cycle. You could see here one example of the test setup. Again, a picture of the test setup. That is the test setup, the DC source and the impulse source in the lab in Arnhem. And the test circuit shown here. So we have used a spark gap to connect the impulse source to the test device. And you could see here some examples of the superimposed voltage stress. So we have used all combinations, so polarity combinations and lightning and switching impulse combinations with a rating of DC 350 kV, lightning 950 and switching 760 kV. For lightning and switching, the values for on-site tests of a GIS was chosen, so that is equal to 80% of the nominal value. We'll continue now with the main outcome, with the main results of the work package 15. So we have reached now, and that is what I can say today, the technology level 8 for HVDC GIS equipment. 8 means only the real service experience is missing. So we have finished all tests in the lab as well as a prototype test. Just 2 weeks ago, we have finished the official part of the long-term test. We are continuing now with some additional PD measurements with a special setup. One major step of our work package was the written recommendations for specifying gas-insulated systems. And we have also defined testing requirements, procedures, and methods for dielectric testing of HVDC GIS based on simulation analysis, of course, and based on real HVDC onshore and offshore experiences, and based and in strong cooperation with the CGRE working group. At the same time, I have not spoken much about that part of our work package, but we have tested alternative monitoring and diagnostic methods of especially partial discharge measurement. Main active part was here the Technical University of Delft. We have used here or developed here a magnetic kind of PD detection in contrast to the conventional capacitive detection on HVAC GIS. And by using this kind of new developed PD measurement, it's hopefully possible to localize the source of this partial discharge as well as a charge estimation. Moreover, we have performed a lot of partial discharge tests with different defects using alternative gases and have compared the results with SF6 with SF6. As an outcome, we can say that from that point of view, there is no reason against the use of other gases for HVDC in gas-insulated switchgear. And moreover, it's possible to use the same diagnostic and monitoring tools for these new gases. We have finished the long-term test of the full-powered HVDC GIS according to the developed test requirements and procedure. And at the moment, we are on the way to summarize everything and to give the input to the different standardization committees. I will show an part here on the next slides. From our point, one of the most important thing is here that we have prepared the terms of reference based on our discussion in our work package and in a special organized workshop dealing with the interface between cable and GIS. Up to now, there is no standard defining this interface, and we have prepared the terms of reference for a new CGRE working group, and the working group is already started, and it's called Recommendations for Dielectric Testing of HVDC Gas Insulated System Cable Sealing Ends. Another important SIGRE working group is this dielectric testing of gas insulated HVDC systems. So we had especially about these long-term test, prototype installation tests, a lot of discussions with the SIGRE working group, and finally we have a common agreement of a procedure for this long-term test, as well as for all dielectric tests. Moreover, we had with the D1 community from SIGRE cooperation dealing with partial discharge detection under DC voltage stress, as well as with the group dealing with the dielectric performance of new non-SF6 gases and gas mixtures for gas insulated systems. And of course, we are also in contact with the new ISC groups dealing with the common specification of DC switchgear, and with the new group dealing with the DC gas insulated switchgear assemblies, which will have the first meeting in end of July. The next slide shows an overview about the different deliverables we have prepared in our work package. The green one you could already download from the web page of promotion. So we have a recommended specification of a DC GIS system, a document describing the test requirements, procedures, and the test methods, especially this long-term test. One report about the diagnostic and monitoring tools in general, and a report on characteristics of a PD in alternative gases compared to SF6. At the moment, we are close to finish the 4 missing reports, and I'm sure that you can also download these reports in latest 6 to 8 weeks from today. Yeah, that's all from my side. Thank you very much.
Yes, thank you very much, Uwe, for a nice overview of activities, and also with focus on how this has been used in already and is used in standardization in SIGRE and IEC and other contexts. There are 2 questions for you. The first one is from Fitim Kriesi, and this is about, do you have at this point 525